All right, we ready? Is there something really exciting going on this morning? Is that where everybody else is at? We're missing out?
Oh,
It's Wednesday? Oh.
You're offering Chem 109.
I am now offering Chem 109. It is. It is at 11 a.m.
That works. That actually.
We'll see. I have to see what room they put me in. I will try to fill the room the best I can. So, yeah, Abigail. I can't, there's no way for me to save spots. But if you find that you are unable to get in, I will do my best to make it happen. So, yeah.
What time are you offering?
11 a.m. So, yeah. So, as of right this second, I'll be teaching, because I feel like a crazy person. I'm going to teach environmental chemistry.
What?
I'm teaching environmental chemistry for EBS majors and Chem 109. Why not? Why not? I was going to teach biochem too, and then that didn't work out. So I was going to teach instrumental analysis, and no one wanted to take that. Made me sad. I got 2 people to sign up for that. I need at least 8 for them to let me teach it. Only 2, and they weren't really crushed, and I told them it was canceled. They were like, okay, that's fine. So. No, it's going to be 109 and environmental chemistry. I'm just doing a lecture. I'm doing the environmental chemistry lecture and lab, and just 109 lecture. So. No, 109 lab is 3 hours. Yeah, no, because the kind of labs they are, they really take the whole 3 hours. Because kind of like when we did lab, 2 weeks ago, when we start with copper wire, and you have to do all those steps, and like by the end of the 2 hours, you're kind of sprinting to finish. The labs are all more like that. So we want to make sure that you have a third hour, so you're not like throwing things around and trying to get out in the 2 hour limit, that you have enough time to really complete the lab without acting like a crazy person. So. All right, let's talk about precipitation reactions. All right, how many people have hard water at home? Anyone? Hard water? Hard water. If you don't know, then you don't have it. Hard water. Like you would know if you had hard water. You would have like solid rings in your tub, and your clothes, unless you do something special, feel kind of soapy. When you wash your hands with soap, they still feel soapy when you're done. Like no matter how much you wash your hair, it still feels kind of greasy. That's hard water. So, hard water contains excess calcium and magnesium ions. That's what causes that soap not to work quite right like it would normally. So, laundry detergent companies have come up with a pretty snazzy way to get around that, so your clothes do end up being clean at the end and not kind of soap scummy. So laundry detergent contains this sodium carbonate, which sodium carbonate it is soluble in water. And calcium and magnesium, they don't come by themselves. They typically come as either calcium chloride or magnesium chloride. Which, let's see if I can find that table. Brought 2 made pieces of paper with me. All right, somewhere you have your table of what's soluble and what's not soluble. And these guys are also soluble. So, in your laundry detergent, you have this sodium carbonate. Which is soluble, so we give it the AQ, which is aqueous. And then you have this CaCl2, which is also aqueous. All right, how many people took square dancing? Totally makes sense. Square dancing. It'll make sense here in a second. Anyone? No one? A few people. Okay, my high school required that we all take square dancing as part of our gym class. So we did 4 weeks of Sweatin' to the Oldies, followed up by 4 weeks of square dancing. Yeah, Buffalo, New York. We also had to do a 6-week unit on gymnastics. We all had to learn how to do an uneven bar routine, a balance beam routine, vault, and floor routines. We couldn't go outside, so yeah. I mean, the liability must have been insane, just because.
Still dizzy?
I'm a little out of practice. I could probably pull together a pretty solid floor routine. Like, you had to do 10 elements. So you had to do like a somersault, you had to do a cartwheel, you had to stand on one leg, stag pose. Totally got that down? Yeah. So, anyway, back to the original question, square dancing. So, in square dancing, right, you can imagine there's at some point you hook elbows with your partner and you're spinning around in a circle, and then the caller asks you to switch partners, and you hook elbows with, like, the partners split up and you hook elbows with the person next to you. So when we do these precipitation reactions, that's kind of what's going on. We have this sodium and this carbonate, right, which are soluble, and they are ions, and we have this calcium chloride, which are also hooked together with their elbows. When the reaction takes place, I'm going to ask them to swap partners. And so the sodium is going to go with the chloride. All right, the sodium was with the carbonate, but now I have the sodium and the chloride stuck together. And then this calcium is going to go with the carbonate. All right, sodium chloride still aqueous. All right, that's just a regular old salt. But if this is called a precipitation reaction where I have a insoluble solid formed from this reaction, guesses on what the calcium chloride state of matter is. It is now a solid. So by reacting these two sets of ions together, I have made salt, which will just rinse away, and this calcium carbonate, which falls out of solution and can be rinsed away from your clothes. And so by adding the sodium carbonate, it gets rid of the issue of the hard water. So it's a pretty neat little thing. So this is precipitation reaction. So precipitation reaction is defined as two reactants produce one soluble and one insoluble product. That makes sense. All right, so what we're going to do is we're going to look at some reactions and predict what the products will be and which will be soluble and which will be insoluble. And because I'm feeling crazy, I decided you guys know all your naming rules. We'll go ahead and just use them as their actual names. All right, let's do this one first, silver nitrate. All right, what is the chemical symbol for silver? Ag. And then what is nitrate? NO3. What is the charge on a nitrate? 1. And oh, I forgot to say, this is silver 1 nitrate. Otherwise, you don't know the answer. Okay, so I got silver nitrate. And we'll come back to states of matter here in a second. All right, what's potassium chloride symbol? KCl. Yep, Cl. All right, so then we have to figure out what the states of matter of both these are. So you're going to want to have your table or your textbook around when you do these things. All right, so I got silver nitrate. All right, so nitrate is under here, salt of nitrate, soluble. So what state of matter should I write it as? Aqueous. All right, what about KCl? Aqueous or solid? Aqueous. Okay. My cues look crazy, sorry. There we go. All right, so those are my 2 reactants. I now need to have them swap partners and come up with 2 reactants. So what will be one of the products? Silver chloride. And then what's the other one? KNO3. All right, so we need to go back to our table and figure out who's a solid and who's not. All right, I got silver chloride. It's a solid. It's right here. Chlorides with silver or solids. What about KNO3? If it's NO3 and it's a K, that's going to be aqueous. All right, how do we feel about that? Good? Does that make sense?
So we have to make them swap, like the first element swap that they go with?
They just have to, yeah, so if you say this is, if these are 2 elements, this silver has to go with the second one over here. I always have the wrong charges. So you always write plus thing, then minus thing. So you have to have the plus go with the other minus thing. All right, let's do lead nitrate, potassium chromate. Oh yeah, question first.
For the silver nitrate, how is that aqueous when silver is an exception?
Oh, because not an exception with the nitrates.
Okay.
It's an exception with chlorides.
Okay.
Yep. All right, let's do lead 2 nitrate. So obviously this is going to be the tricky, all right, as we go down, it'll get trickier. All right, so what's the symbol for lead? PB. And if I give you the Roman numeral 2, what does it tell you about its charge? Right, it's plus 2. Keep that in your head. Nitrate we already had over here. What did we say the charge of a nitrate was? Minus 1. So if lead is plus 2 and nitrate is minus 1, what do I need to do about those nitrates? I need to have 2 nitrates. All right, so this chapter kind of combines a lot of things we've been doing before in terms of charge and balancing. All right. Potassium, we already had potassium. Anyone know the chromate off the top of their head? CrO4. Is CrO4 chromate, is that a minus 1, minus 2? It's a minus 2, so what do I do with this potassium? I need 2 of them. So all that stuff you had on the last test, you know it still. Still, you know, naming and stuff. All right. Lead nitrate. Let's take a look. Is it soluble or insoluble? All right, let's see here. What's your feelings? All right, so here's my nitrates. Are there any exceptions to a nitrate? No, so it's always aqueous. All right. What about chromate? Potassium chromate. It would be insoluble unless I stuck it with anybody in the first column. Those are alkali metals. So this guy is also aqueous. All right, what is a compound you would like to make as a product? Okay, PB. CrO4. All right, we said the chromate was -2 and the lead was +2. So do I need to do anything to this guy?
No,
Nope. Okay, he looks good. All right, so then I have to have KNO3. What do I need to do about that potassium nitrate? Okay, good, right? They're charge balanced. Is my equation balanced? No, how do I need to fix that? Yeah, big old 2 right up here. All right, so now I have to figure out which one of these is the solid.
Lead.
Yes, pretty much anything with lead. Lead will just, I mean, unless it's with the nitrate, but lead, good guess that's going to be the solid. And because it's a precipitation reaction, if you found the solid, the other one's the aqueous.
so you'll always end up with one solid, one
Aqueous, yep.
aqueous
Mm-hmm.
every time?
Yep, so if you can do process of elimination, you'll figure it out. Like if you know for sure, like silver chloride is always going to be a solid. So if you see that, you're like, oh, that's the solid, so the other one has to be aqueous. So, good? All right.
Did you ever start off with 2 solids and end up with 1 solid and aqueous?
I cannot think of a time that would happen, no. I think you'll just about always start off with 2 aqueuses and end up with 1 solid and 1 aqueous. All right, we'll do a few more of these. All right, potassium chromate. All right, so we already have potassium, that's K. Oh, we already have potassium chromate right here. We already said that's aqueous. Silver nitrate, we had that up here. Well, that was aqueous. So what is one of the products you're going to make? Mm-hmm. And we already said that was aqueous. So what must be the other thing you make? Silver chromate, yep. And that must be the solid.
Would you need to,
Oh.
since you have 2 potassium,
Yep, yes.
would it matter if you put the 2 behind the, after the K?
It does, that changes it. So. All right, why don't you guys take 2-3 minutes and do these last 2 ones on your own. Yeah.
Would that be silver 2 nitrate, like in the, with the reactants, like?
Oh, up here?
Balance?
Yeah, it's not.
Let's see here. Yes, yep, I need 2 of those. And then I need 2 of these. Yep. I got ahead of myself. All right, why don't you guys do these last 2 on your own. Sodium carbonate and copper 2 chloride, nickel 2 chloride, and potassium hydroxide.
huge.
All right, looking at my sodium carbonate and copper 2 chloride, what will be one of the products I make? Okay, and what else should I make? Oh, sorry, I meant to leave that blank. The other thing has to be the copper carbonate. All right, which one of these two is the solid? The copper one. All right, looking at the nickel chloride and potassium hydroxide, what is one product I will make? Nickel hydroxide. Is this balanced, this guy? How do I need to fix that? Yeah, I need 2 hydroxides, okay? And then this guy over here. Right, it's going to be KCl, but now I'm definitely not balanced. How do I fix this whole equation? Yep, so I'm going to do a 2 there, and then what else do I need? I need 2 over here. So the trick to these is to charge balance them. Make sure that everybody has the right number of ions in it so that, right, if it's nickel 2, I definitely need 2 chlorides, so this guy's neutral. KOH, that guy's neutral. You make your neutral products and then work backwards to make sure it's mass balanced. All right, which one of these is the solid, the nickel or the potassium? Okay. All right, how do you feel about that? Pretty good? You good? Okay. Alright, so then we need to talk about different types of equations that come. So this is a precipitation reaction, right? I start off with calcium chloride and some sodium sulfate, make calcium sulfate and sodium chloride. I made a solid. So this is overall a precipitation reaction. When we think about this equation, what do we know about ions in water? What do they like to do? They like to stick together or they like to float apart? Typically they float apart, right? But I am showing them as stuck together. So I'm not showing you what's really happening. So a molecular equation shows complete formulas of compounds in their neutral state. Right, you know that calcium chloride is an ion, but it's currently drawn not looking like an ion, right? There's no charges anywhere. It's neutral. In the actual aqueous solution, they're going to break into their component ions. They're going to break apart. So an ionic equation shows all the ions that are present. So a molecular equation assumes that nobody's broken apart. An ionic equation is more realistic. It shows exactly what ions are happening in solution. So let's say, I get a piece. All right, so this is the molecular equation. If I want to write it as an ionic equation, what two ions does this compound break into? Okay, Ca2 plus and 2 Cl minuses. What about this? Right, 2 of these, and what charge would this have, the sulfate? This is a solid, which means it's not going to break apart. So we're just going to leave it as is. And then I have 2 Na plus and 2 Cl minus. This is the ionic equation, right? It's showing all the ions in solution and leaving the solid as a solid, right? Because that has now stuck together, fallen out of solution, so it's not going to break apart. So ionic tells me all the ions that are in solution. What does anyone notice about the way I've now written this equation?
There's no states of matter.
Okay, I got lazy. There's no states of matter. Yeah, let me put those in. I leave myself in the space. Well, these are all aqueous. Whee. If it has a long tail, that means aqueous. There we go. What else? What is true that's happening on both sides of the equation? How many chlorines do I have on this side? How many do I have on this side? How many sodiums do I have? 2, and I have 2, right? So, some of the ions are present on both sides of my arrow. So in an ionic equation, you will have ions that are the same on both sides, right? Because it's balanced, right? They have to appear on both sides. Let me do it this way. All right, so I'm going to finish my thought here in a second, cliffhanger. So chlorine ion is acting as both a reactant and a product. And sodium is acting like a reactant and a product. Can it truly be a reactant and a product? No, because it didn't change, right? Nothing happened to it. Sodium goes in, and sodium pops out. Chlorine goes in, chlorine comes out. So those ions that are present on both sides of the arrow are called spectator ions. They are ions that are necessary to balance the equation, but they do not react with anything. Right, because I didn't make any new compounds with the sodium, I didn't make any new compounds with the chlorine, but they have to be in there to balance everybody out. So they do not participate in the reaction. The reaction being making a solid. All right, in this case, the specific reaction is trying to make a solid. Neither the sodium nor the chlorine participate in making the solid, right? The calcium and the sulfate do. So if they're not participating, they're just sitting on the sidelines, it means I could cross them out on both sides. I could make a net ionic equation, or reaction. A net ionic only shows those ions that participate in making a solid in a precipitation reaction. We're going to talk about other kinds of reactions in a little bit, but for precipitation reactions, only the ions that participate in making that solid are shown. All right, because if they're on both sides, they're not doing anything, you can leave them out. And it doesn't affect the overall equation. So for this reaction up here, the net ionic would just show that calcium 2 plus reacts with sulfate. Ooh. Yep. Right, that is the net overall reaction. The two things that go in make the solid. That's the only part I'm concerned about in that case. All right, so why don't we do at least one example. Oh, we have time for probably 2 or 3 examples of that. All right, so given silver nitrate and magnesium chloride make silver chloride and magnesium nitrate, first question I want is what is the overall ionic equation for this reaction? You may have to write small. It's going to make a lot of ions. All right, so what is the silver nitrate going to break up into? Silver, what charge on the silver? +1. How many silvers will I have? 2. All right, and I'm going to have 2 nitrates. All right, what about this magnesium chloride? What charge will the magnesium have? Plus, how many? +2. And then how many chlorines would I have? 2 chlorines. What charge would they have? -1. All right, silver chloride's a solid, so we're just going to leave that guy alone. And then magnesium. 2NO3 minus. Thank you. Okay. I'll fit on the screen, just barely. All right, so that would be the overall ionic equation. Which ions appear on both sides of the equation? Magnesium does. What else? The nitrates. So, the magnesium and the nitrate are spectator ions, which means when we write our net ionic equation, we leave those out. Which would leave me with 2 silvers. Gonna leave that out, and 2 chlorides. Makes. What can I now do to my net ionic equation? What's left to do to it? Simplify it, right? Because I have 2 and 2 and 2, and I don't really. All right, so this one is the ionic. This one was the molecular, and now this one is the net ionic.
So, on this test, are you gonna ask us like which one does the spectator ions?
There's a 100% chance I'll ask you which one's the spectators.
Write those out to the side.
Yeah, or box them or circle them. I forget how I had it last time. I think it was like, I gave you a molecular, I said write the ionic, and then it was like, circle the ones that are spectators, and write the new net ionic equation, something like that. So, all right, let's do 2 more. Oh, question first.
If you're simplified net ionic equation, plug that back into the original equation, it obviously doesn't balance.
Correct.
Issue?
Nope.
Okay, so it doesn't matter if they're not ionic.
Right. Right, the net ionic is the bare bones version of it. Yeah, there's no way, once you get down here, there's no way to really back up to this unless you knew what the spectator ions were. So, yeah. All right, let's do 2 more. I want the net ionic equations for these 2 reactions. All right, so I didn't give you the products. So the first thing we have to do is predict the products. All right, so if I have aluminum chloride and sodium phosphate, any ideas on what we can make? All right, for sure, we'll start with this one. This one's the easier one. All right, for sure you make sodium chloride. All right, what would the charge on this phosphate be then if I need 3 sodiums? Right, -3. What's the charge on the aluminum if I need 3 chlorides? Right, +3. So I have -3 and +3. Now I just need to balance it. How do I balance this guy? All right, so now it's balanced. Now I need to predict which one is the solid. Sodium chloride or the aluminum? Okay. All right, so that's step 0 to solve this. Step, now we have to write, because that's the molecular, now I need to write the ionic, and then we write the net ionic. All right, so if I write the ionic, right, I'm going to have AL. I'm going to skip the states that matter just because otherwise I run out of space. 3 plus and 3 Cl minus and 3 Na plus and PO4 3 minus makes 3 Na pluses and 3 Cl minuses and an aluminum. All right, so now who are the spectators? Who's sitting on the sidelines? Right, chlorine appears on both sides and sodium appears on both sides. So what is left to make my net ionic? All right, the aluminum's left. That's left. All right, let's do one more, and then I'll save the tricky ones for Friday. Tricky ones. All right, we've had lead nitrate a bunch of times before, so let's go ahead. All right, so if I have lead nitrate and potassium chloride, what's one of the products I can make? I'll give you a hint. It starts with lead. Yeah. Okay. If lead's +2, what do I need to do with my lead chloride to make it work out? Put a big 2 in front of the whole thing? No, just right there. And then what's the other product? Yep, potassium nitrate. Okay, is this equation balanced? No, it's not. What do I need to do to balance it? Okay, if I do that, then what? Is that better? Better? Okay, which one is the solid, the lead or the potassium? Lead. All right, so that's my molecular equation. Now I'm ready to write my ionic. So who are my spectators? Okay, potassium is. Who else is spectating? This guy. Which leaves me with Pb2 plus 2Cl minus makes PbCl2. Any questions about that? All right, next I'm going to save the tricky ones for Friday. And we'll wrap up a little bit early. Unless there's arguments. We can keep going. Strong arguments to continue on? No. Okay.